Okay, so last class we were looking at the diode or the standard form for the, this is called the standard form for the synthesis equation using complex numbers, and essentially we say that a 4 bar can be represented as two diodes, and we looked at just one side of the diode, right. And I will probably skip using the bar, from now on it is understood that if I write this, okay, this is understood that these are vectors or complex numbers. The reason I want to avoid using the bar is in complex numbers the bar indicates the conjugate, so I do not want confusion with that. A textbook they can make it bold, but but in the context of what we are doing you should know that this is a vector equation. So it is an equation, it is two scalar equations, and this is called the diode or the standard form. So how do we apply this to a 4 bar? That is what we will look at today. And then the different types of synthesis problems that we have seen. So let us say a 4 bar is represented by two diodes I say this is Z1, this is Z2, this is Z3 and Z4. This is say point P, and this coupler, okay, I can, once I know Z1, Z2, Z3, Z4, then this Z5 can be expressed in terms of the other two. It is nothing but Z2 minus Z4 if this is Z5, right. So the 4 bar linkage is seen as two diodes. Z1, Z2 and Z3, Z4. So let us say the point P, from the first position it moves to some other point. Let me draw the coordinate system. IY. So I have this is R1, and then at some other jth position point P, so let us say this moves by an angle phi, draw that different color. That moves like that, and so this is P in the first position, this will be P in the jth position, and if this is the, so these two are parallel, okay. So let us say this has rotated by gamma j, this has rotated by phi j. So this one here, the red one, this vector is z1 e power I phi j, this vector is z2 e power I gamma j. And if this is pj, then this is rj. Call this A, B, OA, OB. So Z1, Z2 form the left dyad. This is the right side of the 4 bar, Z3 and Z4. So the point P on the path, on the coupler path, the path point P moves along some path from position P1 to Pj. The positions are defined by R1 and Rj respectively. So that means we have prescribed 2 positions here. So if you have the case where 2 positions are prescribed, which means I know R1, Rj, phi j and gamma j. Well, I don't necessarily know all of them. Let's say, okay, these are the quantities that I require. Okay, so based on this, so now I can write like we did when we derived the standard form. I'll just write down the loop closure equation for this loop here. So I have z1 e power I phi j plus z2 e power I gamma j minus rj, going the other way, plus r1 minus z2 minus z1 is equal to 0. So all these are vectors. Okay, or I have z1 e power I phi j minus 1 plus z2 e power I gamma j minus 1 equal to rj minus r1, which is nothing but delta j. That is delta j. Okay, so this is how we got the standard form. J is greater than or equal to 2. Now let's look at the case of motion generation. Okay, so I have the equation the standard form z1 e power I phi j minus 1 plus z2 e power I gamma j minus 1 equal to delta j. Okay, this is my standard form equation for the left diagonal. Now let me look at the case for motion generation. Okay, let me see whether I should do this. Okay, so for motion generation, what would be the quantities that would have to be prescribed? You need the location of a point on the coupler and you need the orientation of the coupler. Those are the two things for motion generation. So, I need R1 to Rj depending on the number of positions. These should be given. Okay. Similarly, gamma 1, the orientations, corresponding orientations of the coupler are also given. So, if I am given these two, then the synthesis I have to perform is for a motion generation problem. Okay, that is what I am trying to find. I need to find the vectors which will give me this, which will solve this motion generation problem. So, anyway, when we write it, okay, gamma, no, gamma is, j is greater than or equal to 2. It is always with respect to. So, I should say, yeah, gamma 2 to, you will need R1 because you use delta to determine from the first position, but j greater than or equal to 2 means gamma is always from the first position. Okay. So, let us say, let us make a table where I have number of positions, then number of scalar equations for the diode, actually this would be gamma 2 to gamma j, yeah, number of scalar equations, and then the unknowns, the scalar unknowns, or first we will look at the vector unknowns, then the number of scalar unknowns, number of free choices, scalars, and then number of solutions for the unknowns. Okay. So, you can also look at this as R1 to Rj prescribed or delta 2 to delta j prescribed, okay, the displacements of that, and gamma 2 corresponding orientations. So, let us say it is a 2 position problem that we are trying to solve. We know this and we know that. So, how many scalar equations? So, if I write the standard form, okay, my j is 2. It is a 2 position problem. I have position 1 and position 2. So, the equations that I get will be, for the 2 position problem, I have e power I phi 2 minus 1 plus z2 e power I gamma 2 minus 1 equal to delta 2. Are there any other equations? It is a 2 position problem. I get this, a single vector equation which corresponds to 2 scalar equations. What are my unknowns? I have z1, z2, okay, in this equation gamma 2 is given, delta 2 is given, because that is my design condition. I do not know Z1, I do not know Z2, I do not know phi 2. Okay. So, of these Z1 and Z2 are vectors or complex numbers. So, I need, so if I look at the number of scalar unknowns, I have 5. I have 2 equations, 5 scalar unknowns. So, how many free choices do I have? 3. So, the number of free choices is 3, which means number of solutions that I will have is infinity cube. Okay. Take 3 positions. Now what happens? I have this equation, I have, in addition to that I also have this plus, I mean I am using plus rather loosely here, but I will have that equation, I will also have this equation for the third position. Here what are the specified quantities? Gamma 2, gamma 3 and delta 2, delta 3. That is my 3 position problem, 3 position motion generation problem. Okay. So, here now I will have number of scalar equations becomes 4, unknowns Z1, Z2. So, I have all these, basically these 3 are unknown. So, I will just put a ditto, plus in addition to that what else is unknown? Phi 3. Phi 3 is the only other unknown, because again gamma 2, gamma 3, delta 2, delta 3 are given. So, the number of scalar unknowns is now 6. My number of free choices come down to 2, and I have infinity square solutions that are possible. 4 position. Scalar equations, one more. The equations go up by 2. I have 6. The unknowns, all these ditto plus phi 4. Okay. So, this is 7. Number of free choices goes down to 1, and I have an infinity of solutions. Five positions, this goes up to 8, this goes up to 8 again. Okay. So, I am no longer left with any free choices, and we say there are a finite number of solutions. Okay. Not necessarily a unique solution, you would have a finite number of solutions. You do not have an infinity. We will see later when we do that. This is only for one diode. We are talking about only one side of the 4 bar, right. For the other side of the 4 bar, you again have, for the right side diode, Z3 e power I, let us say the angle is psi, like we have been using, plus Z5 e power I, what would be the, sorry, Z4 e power I, what would be the angle of Z4? you are trying to form a 4 bar, it will still be gamma. That is what links. The two diodes are linked together because Z2 and Z4 are going to be part of the same rigid body and they are going to undergo the same rotation. That is how you are building the 4 bar with this diode form. So, e power I gamma j minus 1 and it is still the same point P equals delta j. Okay, so here the unknown, so I can write, make a similar table like this, okay, and in those cases instead of phi it is going to be psi, otherwise the form stays the same. That is why it is called the standard form. Okay. So this gives me what? For if I want to create a 4 bar with these two diodes, it is infinity cube for one diode. This one also it has the same form, so another infinity for a tube position problem, right. So I get infinity cube, I can, so it is infinity to the power 6. Now go back to our graphical synthesis that we did, okay, and see if it is, if you got the same result there. What did we do with the graphical synthesis? So you had two positions, A1, B1, A2, B2, right? And then how, what did I do? I just took the perpendicular bisector of A1, A2, okay, and I picked OA anywhere on that perpendicular bisector. So that gave me how many solutions? Infinity. For B1, B2, pick the perpendicular bisector, I can pick OB anywhere on the perpendicular bisector. That gives me how many solutions? Infinity. So total number of solutions for my 4 bar, yeah. So this is infinity square after I have picked A and B to be the moving pivots. It is not necessary. So I have for A number of choices, I can pick any point in the plane, number of choices is infinity square. For B number of choices is infinity square. Once I pick my A and B, I still have infinity into infinity, infinity square. So for OA and OB, for OA infinity, for OB infinity. So overall I again have infinity to the power 6 solutions for the two position problem. So it does not change, okay, the number of solutions that are possible does not change. What may be restrictive is how you can find the solutions, because if I am working, if I am trying to do geometry, like for the 3 position problem we ended up with a unique solution, right, although this tells me here that I would have more. I actually have infinity square choices for the 3 position problem, but because of the way that we do the construction and the way we choose, so when I choose a point I immediately lose 2 free choices. When we do it analytically, you will see I can possibly choose an angle or I can choose a length perhaps, when we look at solving these equations. that gives you more flexibility, but the number of free choices does not change. Fundamentally the problem will have that many number of free choices because you have so many equations, you have so many unknowns. But the method that you use may restrict you in some ways to on what free choices you are allowed to pick. Okay, and you may have to pick free choices in pairs, like as a point for instance. So then that becomes a little bit more restrictive. So it's more the method that restricts the free choices than the problem is still has that many number of possible solutions. Okay, so that's something you need to keep in mind. Okay, so once we solve the right side dyad, okay, then to create the 4 bar, the coupler is given by, so we'll do it for a couple of problems. So the coupler is given by Z5 equal to Z2 minus Z4. So once I solve Z1, Z2, then Z3, Z4, my coupler is given by Z5 equal to Z2 minus Z4, and fixed link will be Z1, this will be Z1, sorry, should call it Z6 here, Z6 Z1 minus, sorry, Z1 plus Z5 minus Z3 just by the loop closure. So that completely, if I find these two dyads, it completely defines my 4 bar. That's the point I am trying to make. So I can look at the 4 bar as these two separate dyads, design these two separate dyads, put them together to make my 4 bar. So let's look at 2 position motion synthesis. Motion generation. So I have given delta 2 and gamma 2. Delta 2 is a vector. Okay, maybe I'll use the arrow like that. So, and I have my equation for the dyad. We'll keep using that. So I'll write it as Z1 given delta 2 and gamma 2, I have the equation would be delta 2. So what could be my, I know I have 3 free choices. To solve these equations for Z1 and Z2, okay, that's my design, right? Even finding the dyad is what I am trying to do. So to get that, I can say I have to pick 3 free choices now. I have only these 2 equations. I have 5 unknowns. Unknowns are Z1, Z2, let me put it 2 and phi 2. Okay, so total 5 scalar unknowns, but I have only 2 equations. So what I could do is I could pick one vector Have a question? Second equation, yeah, real and complex. It's a vector equation, right? So there are two scalar equations. Ultimately, I have to solve for 5 scalar unknowns. The 2 components of vector z1, 2 components of z2 and phi 2. Yeah, so yeah, just till we get used to it, let me just put that arrow on top of that. Okay, so z1, z2 and phi 2. So now I can choose as my free choices. What are the possibilities? I have to choose how many free choices? I have to choose 3. Okay, so what could I do? The easiest way would be to either choose z1 and phi 2 or z2 and phi 2. So let's say I choose, say my free choices are it's more difficult if I say I will choose z1 and one component of z2, right? Solving the equation will be more difficult. So free choices are this, then I get z1 equal to delta 2 minus z2 into e power I gamma 2 minus 1 by e power I phi 2 minus 1. So this defines my left diode. I can do the same thing for the right diode and come up with the solution for the 4 bar for motion generation. Okay, so this is 2 position motion generation. 3 infinities of solutions with these 2, the choices for Z2 and phi 2. 3 position motion generation. I am given delta 2, delta 3, gamma 2 and gamma 3. So I get and phi 3 minus 1 delta 3. If I go back to my table, how many free choices do I have? I have 2 free choices. 2 free choices. If I do that, then what are my possible free choices are Z1 or Z2 or phi 2, phi 3. To solve these equations, what would be the easiest choices? Phi 2 and phi 3, right? Because if I choose phi 2 and phi 3, this just becomes a linear system of equations. Okay, if I choose Z1 or Z2, one of the two, because I will need 2 components there, right? That would mean that I am solving the equations becomes more difficult because I have all these sin phi, cos phi terms in there. So analytically, it's easy to choose these 2 angles. But imagine in the graphical method, choosing a point was easier. which essentially meant I was actually picking, yeah. So I was taking 2 free choices in that manner. Okay, when I picked a point for the moving pivot. Because when I pick a point for the moving pivot, that kind of defines my z. Okay, assuming I start off at the origin. So I can say that that is my z1. Okay, so that again, number of free choices does not change because of the method that you use, but what you can pick as your free choices, this is not easy to do, picking the angles and then trying to come up with a graphical solution to find the, to synthesize the linkage. So do you see the difference between the graph? Fundamentally they are the same. You have the same number of solutions, same number of free choices. What you can pick as your free choice varies with the graphical and the analytical solutions. So once I do this, I can solve, it's a linear system of equations in Z1 and Z2. And MATLAB can easily solve it for me. Okay, and I can find the 2 vectors. I repeat that for the other side of the 4 bar and I end up with the whole thing. Four position motion generation. We didn't look at this graphically. But let's say analytically we should be able to solve. Phi 3 minus 1 plus Z2 phi 4 minus 1 okay. This is my 4 position problem. So the knowns for motion generation would be delta 2 to delta 4 and gamma 2 to gamma 4 for this problem, and therefore there are 6 equations, 7 unknowns. Unknowns are Z1, Z2, phi 2, phi 3, phi 4. 7 unknowns. 6 equations, 7 unknowns, 1 free choice. So you see, here I could pick one of the angles, but it will still no longer be a linear system of equations. So up to the 3 position problem, the solution is fairly straightforward because you can pick your free choices in such a manner that you only have a linear system of equations to solve. From the 4 position problem onwards, it becomes a little bit trickier. You still have an infinity of solutions. So I can pick one of the angles, phi 2, phi 3 or phi 4, but it is all in transcendental form in the equation, because I can pick phi 2, but there will still be cos theta, cos phi 3, cos phi 4 sine. So it is not an easy system of equations to solve. We will look at a method later where we will do that a little bit later, where we will solve this problem for the 4 position case you can do that. Maybe the 5 position also will do if time permits. But beyond 3 positions you will not get a linear system of equations. The system of equations becomes a non-linear system of equations to be solved. So, this is a system the angles are in transcendental form. Okay. Okay. So, for motion generation, three positions are the limit for a linear solution. So, for the 4 bar, once you solve both dyads, you get the coupler and the so you could have the same routine. Basically, you in MATLAB you would write a routine to solve the dyad form for say 2 position or 3 position synthesis. Call the same routine again to solve the right side dyad, and then put together the 4 bar for your solution.